Hello, Marts here. In this video we should look at something called antiderivatives, and as the name suggests, this is derivatives backwards. In other words, if you know the function we can find the derivative, and the idea is that if you know the derivative we should be able to find the function. One motivation for that is that if we have, say, an ST diagram, we will know that the slope correspond to the velocity. But if we know a function for the velocity, we should be able to find the function for s. As if we know the function for s, we can take the derivative and find the function for the velocity, so we can work backwards. So what we should start with is make a table of some rules for antiderivatives, and we can start with writing rules for derivatives. So if I have my function and I have my derivative, so the derivative, say we have a constant and we know that the derivative of a constant is 0. We can make a corresponding table for antiderivatives. And what we have here is we now have a function, and we must have some way to denote the antiderivative, and we will use a capital letter for that. So to denote antiderivatives, we will use the corresponding capital letter. So if the function is f, capital F is our antiderivative, is our function is denoted by g, capital G is our antiderivative, and so on. We can see here using our derivative rule backwards that if we have a 0 as a function, our antiderivative will be a constant. And we know that if we have an ST diagram and we have no velocity at all, that means that we have a constant position, and that's exactly what this is telling us. If our function has the derivative 0, the function is a constant function. The second rule says here that if we have some mx plus some constant, we know the derivative of that will just be m. In other words, if you have a function that is just a constant, then our antiderivative would be mx plus c. We also know that if we have, for example, one function plus or minus another function, then we can take the derivative separately, the derivatives, and correspondingly, if we have a function plus minus another function, we can take the antiderivative separately. We also know that if we have a constant times our function, I'll write k for the constant here to not mix it up with a c. If we have a constant times a function, we know that we can keep the constant and take derivative, and the corresponding rule here says if we have a constant times a function, the antiderivative will simply be keep the constant and take the antiderivative. The next rule is a little bit more complicated, because we have that x to the power of n gives us the derivative n x to the power of n minus 1. But what will the corresponding rule be over here? And we will find that it'll be x to the power of n will give us the antiderivative x to the power of n plus 1 over n plus 1 plus c. And why and how can we check this? We can always check our antiderivatives by taking the derivative of the result. So if we go in this direction to find our antiderivative, we can go backwards in that direction to find if we are correct by taking derivative of what we have. And let us check this. We take x to the power of n plus 1 over n plus 1 plus a constant, and we will find the derivative of that. Okay, first we can see that this can be written as 1 over n plus 1 times x to the power of n plus 1. plus c, the derivative of that. The reason for this is, for example, that if you have x divided by 5 is the same thing as 1/5 times x. So I just moved the denominator in front of this like this. And that means that we can use the rule that we can keep a constant when taking derivative. So I keep the 1 over n plus 1. And now I need to take the derivative of x to the power of n plus 1. But the derivative rule says that we should take the exponent here, right? And just move it in front. And then we should take the exponent and subtract 1 from it. So I move the exponent in front. N plus 1. And then times x to the power of, and I take the exponent and subtract 1, and that will just give us n left. And secondly, since we can take the derivative separately, the derivative of a constant is 0, so that will disappear. And we can see that these two will cancel, and that will leave us with x to the power of n, exactly as we would expect. So if we take the derivative of this part, it will give us that, and antiderivative should give us the one we started with as a result. So we have found this little rule here. What more rules do we have? We have the e to the power of x gives us the derivative e to the power of x, and that means that the antiderivative of e to the power of x will be e to the power of x, and then I will write plus c here, as I did with other things there. The reason for this is that if we take the derivative of a constant, it's 0, so we'll always add a c. Another way to see that is that if I have, say, a function that looks like this, and I just add a constant to it, so it looks something like this, it won't change the derivative. It doesn't matter where the function is located, it will have this in this direction, it will have the same derivative. So let us find some few antiderivatives using these rules. Okay, so maybe I should move it over here and we can erase all of this. So we have f and capital F, and let's say we start with x to the power of 3, and we can name these rules. Say call this A, B, C, D, and E. So according to rule D, this will become x to the power of 4 over 4 plus c. And you can test yourself, take the derivative of this to see that you actually get x to the power of 3 back. Say we have x to the power of 4 plus x. We use rule B to take the antiderivative separately. So then we use rule D to find the derivative of the first part. So that will be x to the power of 5 over 5 plus, and x could be seen as x to the power of 1. So yet again we can use rule D. So that will be x to the power of 2 over 2, and then plus c. What more could we say as an example? 5x2 plus 4x3. We should take the antiderivative of this. First we have rule B that allows us to take it separately. For the first one, then we have that we have a constant in front of the function. So I keep the constant according to rule C and take the antiderivative of x squared, which gives us x3 over 3, plus we keep the 4. x3 will give us x4 over 4 plus c. We can do a bit of simplification here. Maybe I will write this as 5/3 x to the power of 3 plus, and we can see the 4 and 4 will cancel, so this will just give us x to the power of 4 plus c. Say we have, what more could we say? 3e to the power of x plus 1 over x squared. This is a bit more complicated. We can rewrite 3e to the power of x we can keep, but the second part here could be written as x to the power of minus 2. Okay, so now we can use rule B, which means that we can take the antiderivative separately. And for the first part, we can use rule C. And that means that we can keep the 3, and rule E will give us e to the power of x. And then rule D will say that, okay, that will be x to the power of -1 divided by -2 plus 1, which is -1 plus c, equals to 3 e to the power of x minus 1 over x, right? The -1 we have down here will cause a minus there, and the x to the power of -1 is the same thing as 1 over x, and then we shouldn't forget the plus c. So there we have a few antiderivatives. Hope this helps a bit. Thank you.